Hi, welcome back. So we're in Chapter 3, Descriptive Analysis, still on the discussion of Bivariate Descriptive. Now we have reached out to discuss the second region in this table, and that is when our variable x1 and x2 happens, both of them to be continuous. Let's go ahead and review the study of bivariate analysis in this case. There are different scenarios, and I want you to visualize them before we study actually the relationship. Both axes, this is representing the x1. This is representing x2. We need to look at each subject on its own. For example, the value of this subject happens to be 2 and 3. We call it a vector in its own right. It has a magnitude and it has a direction. So for example, this point here, it has a value on the x1. It has value on the x2 domain. Now, this value is the same. It has value of x1, and it has value of x2 and so on and so forth. I can easily see that as x value go up in values, the direction of x2 also goes up in values. This kind of relation, we call it a positive relation. The opposite, of course, it could be negative. For example, here, this value, the x is quite high here. But if you look at the x2, it's quite low. So that's why it was a negative relation. Different scenario. For example, there is no relation at all. So this is the three possible scenarios. One more thing also I want you to see, it's about the variance or the distance between these 2 points on these boundaries. You could see most of the x1 variables happens to be within this direction, but if you look, you could see that x2 has taken all these values within this. So the variance here of x1 happens to be small, but the variance of x2 happens to be large. Also, vice versa. Let's go ahead and see mathematically how do we actually capture the bivariate relationship. Now, I'm going to introduce you to the first case. It's called the Pearson correlation. We have here x1 and we have here x2, and these are the subject that we always happens to capture. Now, before I take you through the calculation part, which you don't need to do by hand, we have statistical software done it for us. Let me try to graph this. Now, we've got this is x1 and this is x2 variables. Okay. Now the first subject is at the point of 10 and 40. Then we got 12 and 48. Then we've got 14 and 56. And then we've got 8 and 32. Now, if I want to connect the dot, you could see the pattern happens to be in this direction, right? Now, I could easily capture there is a kind of a positive relationship. We need to quantify this. This is the study of covariance as we explored before. The formula actually you might be quite familiar with from the discrete, doesn't really change much, is by taking total summation of the first entry of x1 subtracted from its mean and multiplied by the entry of x2 subtracted from its mean, and then you divide by the total number of the subject. This is x1 and x2, which are the variables here. I captured the mean for each one of them. This is x bar 1 and this is x bar 2. And then I just subtract each value from its expectation. So 10 minus 11 is minus 1, so on and so forth. And same thing I did for the second variable by subtracting each entry from its mean. And now when I want to multiply them together, minus 1 by minus 4, and so on and so forth. After I did, I just sum all the multiplication. And finally, I got 8 divided by 4, I got 4. This is my covariance. Now, to capture the correlation, the equation is as simple as this. Take the covariance values, which we captured already here for, and divide it by the standard deviation of the first variable and multiply by the standard deviation of the second variable, the product between them. Now, to capture the standard deviation, if you remember, we needed to calculate the variance. We needed just to extend the calculation on our table here, the entry minus its mean, and square it, and then take the sum of them. So 20 divided by 4 minus 1, which is 3, come to 6.6. Take square root of that, then you get 2.56. And the same thing I did for the second values here. In the column, 320 divided by 3, that comes 106.7. Take square root, then you got 10.32. So these are my standard deviation. Basically, I just plug in the formula. This is my 4 covariance that I calculated and the product between the both standard deviation. Then you get 0.15. So it tells me that the correlation between x1 and x2 happens to be 0.15. 0.15. This is the quantifying between them. So that was the perception of looking at the covariance and correlation. Let's look at one more case in here. Now, this is another data set I already also prepared for you. And when I graphed this data set, obviously, this is not a linear relation. In the previous graph, there was a linear relationship. But in this graph, we didn't have that linear relationship, but both of them are monotonic in nature. That means they were increasing at a certain point, decreasing at the other point, and there is a behavior you can extract. We use another measure to capture the correlation, and that's called the Spearman's rank correlation calculation. Basically, the formula, it says 1 subtracted from 6 multiplied by the total sum of something called the distance square. I will show you how to capture this, divided by n multiplied by n squared minus 1. First of all, what is this distance? Now, in the first vector in x1, we need to rank them in descending order, where the largest value get rank 1, and then the next largest value get rank 2, and so on and so forth. Same thing you do for the second variable. And after you finish, you calculate the distance by subtracting the ranks. So 5 minus 3, 2, 3 minus 5, it's minus 2, and so on and so forth. And then you take the square of that distance. As you can see, 2 become 4, 4, 1, and so on. This is the total sum of the d squared, which happens to be 12. Now just plug into the formula. You got 12, which is down from here, multiplied by 6 divided by this quantity, then you got 0.9. One more last thing before I close down this section, that we have form of a matrix, covariance matrix. Basically, it's 2 by 2 if it is a bivariate, and it could be n by n if it is a multivariate. What happens in the diagonals here? We capture the variance. And then on the upper of the diagonal, it is the covariance relation. It's a symmetric matrix. The correlation matrix is exactly similar. What happens on the diagonal, the correlation between the same variable is always 1. And here is the correlation value. And of course, again, it is a symmetric kind of matrix. Now we have reached the last region, and that is when x1 happens to be discrete and x2 happens to be categorical, or other way around these regions. Let's go ahead and see what tools that we have to do the analysis in this case. I'll see you then.